And so we can show the electron configurations long or short for atoms or ions. All right, also let's take a minute to talk about some of the d orbitals. So scandium over here, if we wanted to have scandium, well, the last noble gas for scandium would have been argon. So we can say argon 4s2 3d1. If we want to do it for titanium, it's going to look like argon 4s2 3d2. Vanadium, I bet you can see a trend here. 4s2 3d3. When we get to chromium, instinct would tell us that argon 4s2 3d4. But the reality is that it is chromium, argon 4s1 3d5. So what's going on? Well, if I have my 4s and my 3ds, fill 1 electron, fill 2 electrons, fill 3, fill 4, fill 5. And yet, when we go and put our 6th in, like we would 6th element across periodic table for chromium, one of these electrons moves. It leaves the 4s and it goes up. So what is happening? Why does that occur? Well, electrons, when they're paired, it actually takes a little bit of energy to do that. I mean, you're still putting them in the same orbital. You have negative charges in the same position repelling. As a result, there's a little bit of extra energy required. It's called the pairing energy. They don't like to do it. I mean, it's way better than going all the way up to another orbital, but it's not ideal. Additionally, as you have multiple orbitals that are the same shape and energy, so all 3 of your p's, all 5 of your d's, these are called degenerate. They all have exactly the same energy. There's no reason you have to fill one before the others. So let's go back a little bit here when I was filling these. We fill them in line, but there's no difference between them. You can fill them in whatever pattern you want. As a result, as you start to fill them, your atom becomes unbalanced. These orbitals that should all be the same, as soon as there's an electron in one, well, the others are now slightly different. When another electron comes in, it says, well, hey, I don't have all the options. One of the other orbitals is already filled and there's an electron in it, and it's still a negative charge in space nearby. The result is that the energies get slightly different. When you have degenerate orbitals, so all 5d orbitals, but they're partially full, they no longer are exactly the same energy. This imbalances the system. And an imbalance is not ideal. It puts things out of position slightly. So as I add more and more electrons, they're still out of balance, but when I add that 4th d electron, when I get to chromium, it now has an option where it could move one of them and rebalance. Now all of those orbitals have 1 electron in them. Now it is, we say, symmetric. It is balanced again. Even though I had to raise the electron up a little in energy. Well, there's a fight. I had to put a little bit of energy in to go up, but I also lost a little bit of energy because I undid the pairing. And so think about Hess law for a minute, kind of state function. You can go up, you can go down, you can go... It doesn't care, it just looks at where you started and where you ended. On balance, the lower energy of the stabilized set of orbitals plus the loss of the pairing is better than the increase to move it from the 4s to the 3d. Well, these energy levels on the side reflect the energy of the orbital they don't reflect the energy of the system, all of the interactions of all of the orbitals. And so even though it looks like we just moved an electron higher in energy, the truth is the overall change for the system is that it is lower in energy to push that electron up in this case. And so it does. As soon as you now add another electron, though, and go to manganese, well, it's easier to put down in the 4s. You're going to pair it no matter what you do, so might as well go in the lower energy orbital when you pair it. And then as you keep going on to iron and cobalt and nickel, you continue to just start filling. When you get to copper, however, well, this is going to be our 9th electron here. And when I put that in, I now have the ability, I can move that 4s electron again. Well, I want to move the one that's the other spin. What I've done is I've created a set of symmetric d-orbitals again. Yeah, I didn't get the pairing going away this time. So whether it was paired in the 4s or paired in 3D, it's still paired. But I did create a symmetric set of orbitals, which is pretty favorable. Copper will also shift one electron out of the 4s. Your copper will look like argon 4s1 3d10 rather than copper looking like argon 4s2 3d9. Chromium and copper just kind of do this odd little shift. The elements in their column also tend to do this, but as you get further down into tantalum or gold and the like, other complicating factors of f orbitals start showing up. And so we're really only going to focus on these for chromium and copper. But this is a view where we have to take into account more than just the energy of the orbital itself. Where your electron is going to go is dependent on how it interacts with everything. And so our energy diagrams for the orbitals don't always tell us the whole story. These two are examples where changes in the orbital also affect the system in a way that, yeah, an electron in a higher orbital is still favorable overall for the whole system.